1, 2, 3. Mute. Yeah.
Just let me know before we start.
Okay, so good morning and welcome back to the second day of chess, the second session in the second track. So we have 4 speakers in the track today on efficient masking, and the first talk will be on modular nets. Neural networks meet modular arithmetic for efficient hardware masking, and the talk will be given by Anush. So, thanks.
Hi. Thanks for the introduction, Pascal. Hello, everyone. My name is Anuj, and today I would be presenting my talk called Modular Net. This is joint work with Afzal, Dr. Pasha, Dr. Camarota, and my advisor, Dr. Aydin Aisu from North Carolina State University. We have sponsors as the NSF and SRC. Okay. So I believe this is the third day of chess, and we probably don't need any introduction to side channels, specifically physical side channels. We know they're a big problem that needs to be solved, and there's been some wonderful research over the past 2 decades on trying to fix this problem since it was first published in the late 90s. There are papers even in this chess which are trying to provide more and more robust and efficient countermeasures to prevent physical side channels from extracting the confidential data from embedded systems. However, all this research that has been done has been mostly focused on crypto systems, specifically the block ciphers, and very lately the post-quantum crypto systems. We try to do something different in this research work and implement all these countermeasures, or we'll try to see how to leverage all these countermeasures for a different application. And that application is machine learning, which has recently emerged as a prominent field that requires confidentiality. And that is primarily because the machine learning IPs, well, are basically, intellectual properties. They have a value, then that is because of many reasons. The primary reasons being the costs involved in developing these models. So the research and development costs, or the training data that is used to train these machine learning models, which might not always be freely available, and the training process as such, which is so computationally intensive, also requires some specific hardware and investment in that kind of hardware to compute the neural network model parameters and hyperparameters efficiently. Now, that's the first aspect. The second aspect why we need confidentiality is because having knowledge about the model internals also facilitates other attacks, as has been seen in prior research works. For example, the adversarial attacks, which try to fool the model, becomes very easy if we know how, if we're talking about a neural network, how the nodes are arranged, what are the weights and the biases. Model poisoning is another attack which tries to, poison the training data to systematically cause corruptions in the classifications. And of course, fault injection attacks, which will obviously become easier if we know which nodes are important and which nodes are not. So all these reasons build a very strong motivation for trying to extract model internals, and physical side channel attacks, being one of the most potent attacks in today's literature, has been specifically used to extract all these model parameters, not just in theory, but also in practice. This is just some of the research works from the past 2-3 years that have tried to show that you can really extract the model internals by exploiting the physical side channel attacks. So given all this, we asked the question, what about the defenses? And there has been very limited research on defenses compared to all these attacks. Specifically, or well, as far as I can see, when we were submitting the work, there were just 3 research works that tried to implement some form of defense to prevent such model extraction attacks. One of the defenses tried to implement a combination of masking and hiding countermeasures. The second countermeasure tried to implement a fully Boolean masking scheme for a neural network. And the third work, which has been very recently published after our submission, tries to do the same things on a software level. Now, an important observation that we made is, given all these defenses, the early defense research, that we've always been trying to tune the defenses according to machine learning. Specifically, because machine learning arithmetic in general is not really, well, it's not exactly how the cryptographic arithmetic works. It's difficult to directly leverage all the research work in masking to machine learning algorithms. And that has been a big problem. For example, in one of the research works, because of the absence of modular arithmetic, they had to specifically implement a hiding countermeasure to prevent the sign bit leakage. Well, the solution is you can always do a Boolean masking for the entire neural network, but that is going to be extremely expensive because you are trying to perform Boolean masking on arithmetic operations. So given all this, we try to think, can we really try to implement neural networks in a way that is more similar to neural network, to cryptographic implementations? And modular arithmetic being so integral to crypto systems is something that can definitely help us, as we saw in this research work. So we want to implement the neural network operations in a finite structure, like a field or a ring, which is how the crypto systems work. And that can really help us to efficiently implement masking on neural network functions. So here are some of the key ideas of our research work. The training is still performed in floating point. And as we'll see in the threat model, that's because we assume the training to still be performed in a secure environment. Inference is where we perform operations with modular arithmetic. So all the additions that happen in the neural network are performed in some field. And of course, when I talk about modular arithmetic, we need to know what is that modulus. And that had to be fine-tuned using some empirical analysis. And we'll see that in later slides. That causes a very slight reduction of around 0.27% and 0.77% in the MNIST and CFAR datasets. And by doing all these things, by efficient implementation of masking on additions, we were able to reduce the lookup table and flip-flop overheads in the prior solution, which was implemented using Boolean masking by 45% and 38%. Now, before going into the details, I'd like to briefly touch upon some of the specific preliminaries, specifically binarized neural networks, which is what we target for this work. These are special neural networks which have the weights and activations binarized to be only +1 or -1, and that enables very, very efficient hardware implementations because the computationally intensive floating point operations are just converted to bit level operations like XNOR and pop count. And this has been recently gaining a lot of, these have been recently gaining a lot of popularity even in industry. And thus we believe that this is a good starting point for research on side channel countermeasures for machine learning. And that thus I present my threat model, where, as I said, the training phase is trusted and the trained secret model parameters are deployed on a device which is running in an untrusted environment. So the device, the adversary, just like a differential power analysis, can observe the inputs and the outputs, and of course the power consumption, and can run some kind of a statistical power analysis to extract the weights and biases. Here specifically, we are targeting the parameters, or we assume that the adversary targets the parameters. The implementation is constant flow and constant time in hardware, so that makes attacks such as timing and memory side channels out of scope. And the platform, yes, as I said, provides power consumptions to be obtainable, but invasive attacks or tampering attacks are again considered out of scope for this particular work. Third, domain-oriented masking. I guess we have had a lot of masking sessions and we probably know the structure. So this is one of the masking gadgets used a lot in crypto systems. This is secure in the glitch extended probing model because the cross-domain terms are refreshed and then registered, which ensures that the glitches do not unmask the unshared secrets. The problem, one special thing that we had to do in our work for DOM gadgets was to also register the outputs, because without registering the outputs, a glitch extended probe can extend to the first partial product, and in the second gadget can combine the two secrets to leak the information. So all the DOM gadgets, whenever we feed to a nonlinear gadget, is registered before that operation. Okay, so modulo net, which is our work. So to find the modulus value, we tried to plot a histogram of how the weighted summation distribution looks at the input of each neuron. And as you can observe, because we have an assigned representation here, it's kind of distributed around 0. These negative values will be binarized to -1, positive values will be binarized to +1. But with modulo, the negative half of the histogram shifts to the positive side, right? Because that's how modular arithmetic works. And because of that, what was a sign function now becomes a threshold function. So we had to make that first change. This was good for hidden layers, but what happens in the output layer is the distribution is not really uniform around 0. And we actually observed that it changes to two peaks, the peak corresponding to all the incorrect confidence scores and the peak corresponding to the correct confidence scores. And when we apply modular arithmetic, the incorrect confidence scores actually shift on the positive side. And because in the output layer, we basically compare all the confidence scores and check which is the maximum, we cannot do that anymore in this distribution, right? Because if we directly put a max function on this, these scores would be incorrectly classified to be the correct scores. So we changed our output layer function to instead compute the maximum first below a certain threshold. And if that max doesn't exist, only then compute a global maximum. And we also tried to see how the modulus varies to find what is a good modulus value for the specific data sets that we work on. And as you can see, around 2 to the power 15, it was not giving us any more returns. So we reached the point of diminishing returns after 2 to the power 15. We are restricting it only to 2's powers because that's efficiently implementable on hardware. Now I'll discuss how the output layer was designed in using masking for our specific use case. So as I said, we first need to perform mask. We first need to compute the max below a certain threshold, and then we need to compute a global max. And all these operations are highly nonlinear, which is why we first convert the arithmetic shares to Boolean shares using an arithmetic to Boolean conversion. And on these shares, we filter the values that are below the certain threshold, which then go into a comparator, which is also masked. And the comparator basically compares which of the scores are the highest scores. And based on that, a multiplexer selects the shares corresponding to the highest confidence score. In the second round, which is controlled by the P2 bit, the thresholder is bypassed, and I directly compute what is the maximum confidence scores, which is given by the global max register. And all these components internally, the thresholder, the comparator, and the multiplexer are implemented using DOM gadgets. I always register the inputs at the output of the DOM gadget whenever I'm feeding it into the next nonlinear gadget. For the comparison, one quick comment here. So masked comparison is used a lot in the context of lattice crypto, and there the comparison generally means equality. But here we had to really compare the magnitudes of the two shares, right? So it's like a bit by bit comparison, which we implemented using a logarithmic. The structure is very similar to a Cogestone adder, where we would compute the bits from the most significant bit to the least significant bit. Secondly, the thresholder, which basically checks if something is greater than 0 to bypass, and if less than 0 to 0 out, is also the functionality of a rectified linear unit. So this gadget can also be used as an ReLU in neural networks that use ReLU as the activation function. Coming to the overall design, as we can see, we perform arithmetic masking before the weighted summations. So that's the pixel value that comes in PI. It gets arithmetically masked, and then it gets multiplied by the weights. The weights then feed into a weighted summation. There are two independent data paths there, and these weighted summation shares then go into the masked activation function, which compares which of these, which basically binarizes the weighted summations. Here we implemented it using a masked Cogestone carry propagator to compute the Boolean shares of the MSP. Now, because we convert to Boolean shares here, but in the next layer, we again want to perform arithmetic masking. We need to convert these shares back from Boolean to arithmetic masking, and that is why we need a B2A converter. Finally, in the last round, the values go into the masked output layer where we get the inference output. We also implemented a binarized convolutional neural network. And here the initial part is still the same with some changes in the read logic because we are performing convolutions and not a straightforward weighted multiplication. But one thing that I would like to note here is that we also have an additional operation called max pool. So max pool tries to pool the values in a certain window. It's basically a subsampling technique. And for binarized neural networks, max pool is essentially an OR operation. An OR can be masked easily using a masked AND, but that adds an additional latency, and that would create bubbles in the pipeline. But since multiple max pool windows are independent of each other. What we do is, while the first max pool windows outputs are being computed, we can pipeline that with the other max pool window computations and ensure that we do not lose any cycles in the overall throughput. And it's exactly equal to what was the throughput without the masked max pool gadget. These are our TVLA results. We perform both TVLA on the individual gadgets, the activation functions, the comparators, the conversion circuits, both in the unmasked format and the masked format, as is usually done in the side channel literature. And the figure on the below is basically the one with the overall inference. As we can see, when we unmask, so when we are zeroing out all the PRNG outputs, we do not see any leakages. But when we implement our countermeasures or activate them, we do not see any leakage with 2 million traces combined in fixed and random data sets. In addition to what I already presented, we have more details in the paper on the masking gadgets, how we actually implement them, the security proofs of those gadgets in the glitch extended probing model. And we also did TVLA evaluations for the convolution and max pool layers. To finally conclude, machine learning, as we see, provides a new avenue for side channel research. Defenses have been relatively less explored, and this whole idea of trying to transform the neural network functions to be similar to cryptographic functions can really help us to efficiently implement masking countermeasures. And of course, I only did it for binarized convolution and MLP layers, but there is certainly more scope for other ML topologies, such as the recurrent neural networks and LSTMs. So yeah, with that, I'd like to conclude my talk and have any questions. Thank you.
Okay, do we have any questions from the audience?
So thanks for the nice talk. Can you hear me or?
To some extent, yeah.
Okay. So my question is, did you try any formal verification tool or any simulation-based tool to check your designs?
You mean something like Silver or yeah?
Yes.
So for this work, we have done this manually, but yeah, that is something that we could have done. I guess when we were kind of submitting and starting this research work, Silver just got published, and we did not have time to perform formal verification on those gadgets. But that is certainly something that we can try and is going to happen for future.
Do we have any other question? Okay, so maybe I also have a question. I saw that you have, I think, 2 types of networks where you applied your idea on. So what do you think? Is it scalable? Can you also apply this idea of modular net to any other kind of network type?
So I think, yeah, the techniques can certainly extend, because the neural network operations, at least the neuron computations, are still going to be the same. We have also applied these techniques on lower quantization levels, that is 4-bit and 8-bit. And there what happens is the binarized multiplication is actually a regular multiplication. And that is obviously going to now increase the cost to some extent, because now we need to mask more bits. But the technique as such is definitely scalable.
Okay, thanks. So maybe time for another quick question. If not, so let's thank the speaker again.
Thank you.
So the next talk will be given by David, and the title is hopefully showing up soon.
Yeah, hello. We also want to make a quick announcement. This beamer will not be fixed till next session. So for the next 3 talks, this will not be turned on. So anyone that's sitting and cannot view the other projector, well, you can move now or open in Zoom and mute your audio and check the presentation that way. Thank you.
It's not the title. I can also not. Oh, it's fine.
Okay, so the next talk will be composable gadgets with reuse fresh mask, first order probing secure hardware circuits with only 6 bits of fresh masks. And the talk will be given by David.
Yeah. Thanks, Pascal, for the nice introduction. So I'm going to give a talk about a work I did together with my advisor, Amir Moradi at the Ruhr University, Bochum. And in essence, the work is about, or the work proposes new types of gadgets that are freely composable and that can mask an arbitrary logical circuit under the first security order, and introduces only 6 fresh random bits in total to the whole design. And here, note that we don't count the fresh random bits needed for the initial masking, but only the fresh random bits needed for the masking the circuit itself. Yeah, and usually this composable hardware modules, you refer to them as gadgets. So we called our new gadget construction composable gadgets with reused fresh masks. And maybe a disclaimer, a lot of the information will sound familiar, especially if you visited my first talk yesterday, but I anyhow give a quick recap so it's fresh in your mind. So masking is a long-standing countermeasure against side channel analysis. And so the underlying principle is we split the secret into shares that are uniformly drawn and independent of each other, and then we perform the operation on these shares instead of the secret itself. And intuitively now, because of the split in information, the adversary needs to get information about all the shares when he wants to get information about the secret. So any part of the shares or any subset does not help. And how does the masking scape look like? So we can broadly divide the space into 2 categories. The first one is the masking on an algorithmic level, so on a more global level, where the engineer or the researcher tries by dividing the logical circuit into functional blocks and cleverly introducing with flash layers. And by this trying to mask the cipher, and at the end, kind of heuristically arguing about the side channel resistance of the overall design. In contrast to that, we have the gadget-based masking, which is a more systematic divide and conquer approach, which is based on these composable gadgets, so these composable hardware modules that if we that guarantee if we compose them together to a larger circuit, that we can be sure that the circuit will be provable secure in the corresponding adversary model. And the advantages of this approach are that it's completely automatable. And yesterday we heard a talk by Amir. There's this tool Agema who already does exactly that. And it can be, so we can mask arbitrary circuits for arbitrary security orders. And as I said, like the overall circuit is provable secure in the corresponding adversary model. Now you would think, okay, cool, everything is automated, masking is solved, so we all have no job anymore. But essentially, like there's a drawback to that. This gadget-based masking introduces an high overhead into the design with respect to randomness requirements and latency and also area overhead. And especially when we compare it to this more global approach, these typically result in a more optimized design. Now, our approach is settled in the gadget-based masking, where we try to reduce the randomness requirements of the overall design. Now, to formally argue about side channel resistance, different adversary models were introduced over time, working on different abstraction layers. And a very convenient one is the deprobing model, where the adversary can place up to deep probes onto wires of the circuit, and then he should not be able to learn anything about the secret itself. And it was later extended in form of the robust probing model, which also captures physical defaults like glitches, transitions at register stages, and coupling between wires. And this is very convenient because with this model, we can already very early in the development and production stage of a circuit argue about the side channel resistance. So typically we can already argue on the netlist level about the side channel resistance of a design. Yeah, and for us, so our construction, our gadget construction will be at the end secure in the glitch extended robust probing model under the first security order. So we consider glitches occurring in hardware and D equals 1 here. So the adversary is able to place one probe onto a wire of the circuit. Now, what are glitches? Glitches are unintentional signal recombinations in a logical circuit caused by different path delays between two register stages. Now, this might cause the adversary to not only get information about the stable wire or the value of the stable wire, but also getting values about all stable values contributing to the wire, to the value of the wire. And this is captured in the robust probing model in a worst case manner. So actually our standard probe is simply replaced by a stronger set of probes at the register stages. And by that, the adversary is able to probe every stable wire contributing to the initial wire where the standard probe was placed on, originating from the beforehand register stage. Yeah, and now how does the concept of this gadget-based masking look like? So actually, it's very simple. We have our library of composable gadgets, and then we have our unprotected circuit. So the gadgets in this library may fulfill a masked variant of an AND or an OR or something, and then we would just replace the unprotected gates in the circuit with our masked gadgets, and then we can be secure, and then we can be sure that we are side channel resistant in the corresponding adversary model. And the drawback of that is, for example, if you would use HPC2, which is a composable hardware gadget under the Piney notion, so it's essentially freely composable, then you would introduce gadget individual fresh masks for every gadget instantiation. Yeah, and for example, if we would have a design where we have 7 AND gates in total, this would already lead to a scenario where we would need 7 fresh random bits in the circuit, in the masked circuit. And note that these random bits have to be renewed every clock cycle. Now, of course, if you have only 7 AND gates, this is not that relevant. But if you consider, for example, a round-based AES where you have up to 700 AND gates, yeah, this becomes more and more relevant. And you, as I said, you have to renew these random bits every clock cycle. So you will essentially need a PRNG that has this high of a throughput. Yeah, and now our question was whether we can kind of build gadgets that eventually will reduce the overall randomness of the resulting design. And our idea was to build gadgets where we can reuse the same randomness in every gadget instantiation. And yeah, with our new construction, our coma gadgets, the scenario looks different now. We also replaced every gate in the unprotected circuit with our coma gadgets, but now we can essentially reuse the same 6-bit of fresh randomness in every gadget instantiation. And already at 7 AND gates in the unprotected circuit, we have an advantage because now if we have an additional AND gate in our unprotected circuit, we would not introduce any additional randomness into the design, while comparable gadgets like HPC2 would introduce an additional random bit per gate into the design. Now, to construct these gadgets, we asked ourselves, okay, why is this fresh individual randomness necessary in the gadgets? And the kind of the intuition behind that is that we want to argue about probe dependencies between the probe and the input, independent of the surrounding circuit, so in an isolated way. If the randomness here in this example, which is a very simple example, let's consider this gadget where simply the first input share is blinded by R and stored in a register. Now, if R is completely independent of the surrounding circuit and freshly drawn, this P, if we place a probe on this value, will not give us any information about the input. Yeah, so we can kind of argue in an isolated way on what input values the probe P depends. Now, if we reintroduce, or if you reuse randomness, the situation might change. If you just consider GHBC gadgets, which I introduced yesterday, where one output share is simply the secret value blinded by a fresh random bit. And this would be now the first input share to our gadget here. And we would reuse the same random bit in our gadget. We would simply unblind the secret and the probe could simply observe the secret. So we may have to make sure that intuitively that the input is kind of independent of the randomness we use in the gadget to be able to argue that we are not unblind the secret. So no single probe is able to unblind the secret at the end. And with our Komar construction, we do exactly that. So here you can see our 2-input AND gadget, where we simply have this input refresh and we have an output refresh where we refresh every cross domain. And now we can be sure that the output will be completely independent of the fresh random bits used for the input refreshing. And intuitively, this allows us to argue that a secret value is never unblinded, regardless of where we place a probe in the circuit. If we use only Komar gadgets, then the input will be either an initial input or it will be an output of another Komar gadget, so completely independent of R0 and R1. And then we refresh it at the output and have the same situation again. So this is the intuition. And we also constructed an Xor gadget, which follows the same general structure, right? We have this input refresh and we have this output refresh, where the output refresh again ensures that the input bits are completely independent of the input values. The input refresh values, random values, are completely independent of the input values. Now, we not only considered 2 input gates, we extended our approach or our construction to also support arbitrary input width, so an arbitrary number of inputs, which exactly follows the same structure. We have this input refresh, and then we have a refresh of every single cross domain. So we at the end result at these n fresh random bits at the input and the 2 to the power of n fresh random bits for masking the cross domains. And now, if you would mask an overall circuit, the number of fresh random bits we need is simply n plus 2 to the power of n fresh random mask, where n is the maximum number of inputs in any of these gadgets. So the largest gadget is determining the number of fresh inputs we need in the overall circuit, because we can essentially reuse parts or the whole random bits in every gadget instantiation. Yeah, and now is it worth it? So we have one major drawback here, because in comparable composability frameworks, the linear operations are essentially for free. You can just mask them in a share-wise manner, and you will not introduce any additional latency or randomness requirement. And for our Xor gadget, we need 2 register stages latency. So if we compare us to these gadgets, we will result in a much higher latency requirement. But at the end, we drastically reduce the randomness requirements, because regardless of the size and the complexity of the unprotected circuit, we only need 6 fresh random bits in total. Now, our construction of the multiple input gadgets kind of mitigate this problem, because if you would, for example, think of an n combination of 7 variables, if you only use 2 input AND gadgets, you would need this tree structure with an logarithmic depth, and that would introduce a lot of latency, and we can just do it in an n input width gadget, which only introduce 2 clock cycles latency. But at the end, if we also only use 2 input gadgets, we are much worse in terms of latency. And this you can see here. So basically, we have a drastic improvement in the number of fresh random bits we need per cycle. Yeah, so we conducted several case studies. We integrated support for these gadgets also into Agema, the talk you had yesterday, and we can fully automated generate or mask any circuit we want. Yeah, so we made several case studies, and here you see a round-based AES implementation, and we only need 6 fresh random bits per cycle, while for example, DHPC or HPC2 gadgets need 680 bits per cycle. Now you also can see our disadvantage in the latency. So we have 42 clock cycles added latency per round, while comparable gadgets have like 8 or 4 even. And if we don't compare, or if we don't consider the randomness source for generating the random bits, we are also worse in the area requirement or in the area overhead. Yeah, but if you have a lot of fresh random bits, you need PRNGs with a high throughput, which also introduces an area overhead into the design. So it wouldn't be fair to not consider this. So we did another case study where we actually built the randomness source here, and we considered different architectures. We considered the PRNG based on an LFSR with 31-bit width and one LFSR with 34 bits, and also one Kedjak. And here you can see at the end, if you consider both, the area overhead for the actual circuit and the area overhead for the randomness source, at the end, we actually do have an advantage. Of course, this cannot be judged as a general rule. There might be more clever ways to implement the PRNG, but I think it's a reasonable approach and gives kind of a fair comparison here. Yeah, so the takeaway is, again, we are much better in terms of randomness introduced, and also in overall, we're also better in overall area, and the price we pay here is latency, essentially. Yeah, thank you very much. That's all from my side. I'm happy to take any questions.
Thank you, David, for the nice talk. And we do have some time for a few questions.
Thank you. Thank you for your talk. Did you investigate the price in terms of security of using only 6 bits in the whole design?
You mean whether we made some actual security evaluations at the end?
Or if you have some security loss by only using 6 bits of randomness for the full mass circuit?
So we conducted actual practical leakage evaluation, and multiple one of them, and yeah, at the end, all of them were secure with 100 million traces. So yeah, this actually works in practice.
So you tried like to detect for first order leakage, right?
Exactly.
Okay.
And
but did you consider like horizontal attacks or multivariate attacks, this kind of thing?
no, we didn't consider that, but you are right. If you like have multiple points in time where we can kind of reduce the randomness, this might be an issue at the end, but we didn't consider this in the scenario.
I think it would be interesting to
see, yeah.
to investigate that and see some compromise between the overall randomness and security against this kind of.
Yeah, I agree. Thank you.
Hi, nice talk. Probably I've missed it, but is it trivially composable, or is it, or?
Yeah, it's trivial. You can freely compose it trivially. So if you only use,
So
it's not composable with like other gadgets from other composability frameworks like Piney or something, but it's trivial composable in itself. If you only use Coma gadgets, you can just construct gadget circuits like you want.
Okay. Okay, thanks.
So related to the question of material, like in your implementation, do you use the same bits for the full AES, or do you change these random bits at every cycle still?
We changed the bits at every cycle.
Okay. And quick question: did you consider higher order masking?
Yeah, that's an interesting that's an interesting question. Like you cannot consider it in the direct manner, right? Because if you would reuse randomness in every gadget, you could just, if you have 2 probes, unblind everything. but actually you could think of reusing a part of the randomness. And actually I can do some advertisement. So tomorrow is a nice talk by Jakob, our colleague at the Ruhr University, and there we try to reuse the fresh randomness in higher order gadgets, existing higher order gadgets. Exactly.
Okay, do we have more questions from the audience? There are still no questions on Zoom. If not, then yeah, let's thank the speaker again. And the next talk will be given by Wei on the topic of inefficient and secure code-based masking, a pragmatic evaluation.
So which ones? Okay. Hi everyone. I'm Wei Chen from Telegram Paris, and this is a joint work with Qianbei and Sivan and Fan and Lazarui from Zhejiang University. Our work is about efficient and secure code-based masking implementation and also attack-based evaluation. So firstly, as a trace participant, so we familiar with side channel attacks, but just one sentence. So basically, any physical computation performed by real device, it will leak some observable leakages that could be used for attacks. And basically, the masking is one of the most famous protection against side channel attacks. So basically, it has a probable security, and the cost is acceptable, and it's algorithmic level, so it can be flexible to any algorithms. And the most simplest one is Polyamasking. So basically, so here we use just AND, but it's XOR infinified. So for the Polymasking, we have the first chain is the sum, the XOR of all the masks, masks Y and X is sensitive variable, and then Z is the encoded variable. So this scheme can be generalized to the code-based masking, in which we have the uniform representation, which is Z is XG plus YH, where X can be more than one byte or one word, so it's a kind of a packaged implementation. And then we have unshares. So here the most important stuff is J and H. So there are two matrices. There are generator matrices of linear code C and D. So we only consider linear code here. And the condition for this construction is that the two linear code C and D, they have only 0 code word in the intersection. Otherwise, we cannot decode the security. And then for so if n is equal to k plus m, then it's then no redundancy, and if n greater than k plus m, like a polynomial masking, it can be redundancy. So that's the basics. So here are two examples. The first one is Boolean masking. So it's the same as before. So we can express in coding theoretic form. Then it's G and H are very simple. It's binary matrices. And then if we move to inner product masking, we have one minor changes, which is AI is here. It's a constant. And then in the matrices of H, we have the first column is different. by this way, we can have a very nice property that the transition leakage can be removed. We believe it can be removed. So we have two examples here. So, however, we have maybe more than two issues, but in this work, we focus on two issues. The first one is high computational overhead. Basically, for instance, for improved inner product masking, it's about 1.5 times to Boolean masking. And for the cost amortization works, it works better for only for larger n, but for n like 2 or 3, it could be inefficient. And the other one is okay, we have many constructions, but most of them are theoretical analysis or it's only by simulation. So and a few of them did some test for leakage assessment, but without further attack-based evaluation. So in this work, we focus on both the efficiency and the security evaluation. Basically, we choose this big matrix as the encoder. Basically, it's a concatenation of J and H. Then we could choose any of the elements in this matrix. The only condition is that the C and D, two linear code has only the 0 code word in the intersection. So basically, we could choose that J is identity plus 0 element, and then here we have a read part, then it's another identity. So by this way, we could have as many as 1 and 0, then the sum of multiplication can be removed. So our improvement, so firstly, it's valid because J and H matches with this condition, and it's also generic because we consider any could consider any linear code by equivalence. We could take the systematic form, then it could be like this form, and also it's a species, so we could remove as many as multiplications. Then we record the multiplication in the chess 20 paper because so this one is the only one consider the general code-based masking, and for any encoder. For linear operation, because it's much easier, so here we only consider the multiplication, non-linear part. So basically, in this framework, we have like input is 2 sharing, x hat and y hat, and then by out product, it's like the same in ISW scheme. It's out product or tensor product. Then it's refresh and to get S with the multiplication with this matrix M. It will interesting. It will transform to Boolean sharing or additive sharing, and then by re-encoding, it will go back to generally code-based masking. So then after refresh again to go to output. So basically, what we could improve is that because we take the encoder as this, so we could remove 0 part in the refresh to refresh part. 0 part, and then in the M matrices, there are n M matrices. So we could only choose the first K column. So afterwards, this matrix could be reduced, and then we can see that by multiply with this generated matrices, it's equivalent. It's almost did nothing, and it's equivalent to this one. So what we need is only concatenation of 0 parts to the end of to get W matrices, then to refresh again. So that's our improvement. So here is a comparison of the computational complexity and also the visual comparison. So for instance, so just one note. So here the L gadget is for performing the linear operation. In the construction, they use the same framework as in this multiplication gadget. So we denote as A and B. So we can see that the red curves are ours with k equal to 1 on the left and k equal to 4 on the right. And then we count the number of multiplications. We can see that it can be improved a lot. So to save the number of multiplications. Next, so we consider another case that is, so if we want to protect multiple sensitive variables, like a k is greater than 1, but we still want smaller value of smaller security order, like m is 1, it's only one mask. M is 4, then it's can be false order security. We can see that if m is small, the cost, the packaged implementation could be very inefficient. But when m is much larger, these two curves will uncross. Like if m is greater than 5 or even much larger, so it will uncross at the end. Like if if m is like 16, then it's the packaged implementation could be very efficient, much efficient than the linear one. So here is the implementation comparison. So in our case, we consider ARM Cortex M4 device. In the baseline, it's AVR implementation, and we have like so. The interesting thing is that here, if we take the reference, the overhead is about 1.5 times to Boolean 1, but in our case, it's about 1.2 times to the Boolean masking. So that's our implementation part. So next we move to evaluation part. So basically we could consider three types. The first one is the no redundant. That means n is equal to k plus m, and here we take k equal to 1 and m from 1 to 2. Then it's packed type. It's when k is greater than 1, but for the simplicity, we take n equal to k plus m, then just change k from 1 to 2 and 4. So the last case is redundant. That means, like for instance, in Boolean masking, we only need m masks to achieve m's order security. But here we could increase the number of shares, but not in Boolean masking, like in the presentation by the previous session. It's by using encoding, we could increase the number of shares to get larger, much larger implementation. But so here, because the redundancy is very important for detecting the photo, because the implementation against photo injection. So it's interesting to have this comparison. And our target is it's not only encoding part but also computation. So for the encoding, we consider the sub-byte in the first ASIC round, and for the computation part, we target the bottleneck, security bottleneck part, which is the matrices T in the L gadget, as we showed before. It's a Boolean sharing. So before we go to the experimental result, we identify security bottleneck. So we don't say it's a flaw, because it's not a flaw. It's still SNR. It's still secure on the probing model, which has SNR security, but it's because we first from code-based masking to Boolean masking, then by re-encoding to code-based masking, then there is a transform from back and forth transformation, We call this as a security bottleneck. So we will show the results afterwards. So for the evaluation, we consider TVI as the leakage assessment, and the text we consider second order CPA and also the test of time template attack. For the experimental setup, we choose the ARM Cortex for the device legacy STM32F407, and we use the EM traces. So here is the setting of encoder. Basically, we consider first order Boolean masking and second order Boolean masking. And for IPM, we only consider two chains. So the only difference is here the parameters IPM 2 is 2 and 14 is 14 at the end. So by taking the chess 2021 paper, we could predict the security level is from Boolean masking to IPM2 to second order Boolean masking, and then to other cases. And the last one is one of the optimal linear code that can be found in this case. So here is the evaluation of second order CPA. We could find that there are two cases that cannot resist to second order CPA. And for the others, especially for three cases, for IPM3 and 14 and 23, they can resist second order CPA because in fact, the security order could be like third order or fourth, at most third order, I think. So it's interesting to validate the security order amplification that has been like 5 or 6 years in the literature. Next, we present the result of template attack. Then we could find that the security level here is from first order Boolean masking to the last one is IPM 2023. So it's exactly as expected. So here the security level we don't say it's a security order because security order is almost like under probing. It's almost the same, but practical security order when evaluated by success rate or case entropy, it's much many differences. So it's again it's useful to validate this property and to have a practical verification of theoretical results. Next, we try to validate the security bottleneck as we identified before. So it's basically it's a code-based masking transformed to Boolean masking, and then go back to code-based masking. But if we target the T matrices, which is only Boolean masking, we could find that all the cases will clash to the Boolean masking. So it's that means if we cannot fix the issue in the transformation, there is no meaning to use code-based masking because it's almost the same as Boolean masking. So this is a no redundant type. So next we move to amortized type. So basically we only consider Boolean masking, but we could use multiple key, like a key equal to 2. We mask two chains, two pieces of sensitive variable. Once it's kind of a reuse of random masks. So the encoder is very simple as here, and we could also predict the security is from this one is much could be much security than the others. So basically, this is a t-test that we could find as the one did by the previous session. It's we could find the mainly transitional leakage from Boolean encoding. So that's bad news because here we consider software implementation, so traditional leakage could appear. And then if we move to, because it's only first order masking, so we consider second order CPA that could succeed. We could find that because we could find more leakages and to recover several like a kbyte of information, so we could improve the attacks. At last, we consider the redundant type of implementation. So here the encoder is similar to IPM, but we consider more chance than only taking IPM. So here we take 3 chance and 4 chance, but still the security order is the first order on the probing model. The interesting thing is in TCHS 21 paper, they establish the connection between the due distance to the side channel resistance. Basically, for these 3 parameters, they could have due distance equal to 4 in two-share mask. But in fact, if we come like in a redundant type, it's combined, then it's the due distance could only be decreased. So as in the previous one, we could predict the security level is from IE2, IE1 to IE2 to IE3. And here is the evaluation. We could find that also, so basically here is the IPM, it's IPM 23 as before. Sorry. So as before, so IPM 23 with 20,000 traces is like this one, but with the one redundancy, it goes to read one, and then with the two redundancy, it's like a yellow one. That means if we consider combined countermeasure against both side channel and photo injection, then the case is if we add more redundancy, it could need more leakages from side channel perspective. So that means we need to make a condition we need to make a trade-off between the side channel resistance to photo injection resistance. So to summarize, we propose improved constructions for multiplication gadget and also the implementation. We provide security evaluations for 3 types of code-based masking, 3 kind of instance, and also we identify the security bottleneck. So for the future work, we would like to construct fully code-based. That means we would like to find another way to remove the back and forth transformation. And secondly, as code-based masking is a general scheme, so we could try to find applications to lightweight and also post-quantum implementation. That's the talk. Thanks for your attention.
Thank you for this nice talk. We do have time for 1 or 2 quick questions. So we are slightly over time. Do we have questions? Okay, maybe I have a quick question. So in the end, you mentioned that this idea that there's a drawback with the redundancy. If you're using redundancy for fault protection, this actually reduces the security of the side channel protection.
Yes.
But do you still see room that we can use this idea for combined protection? So do you have any idea how to mitigate this?
Yes, I think it's interesting to have this result regarding the redundancy. Basically, if so, the possibility, like for instance, if we choose optimal linear code to maximize the due distance, etc., to maximize the protection of side channel, and then if we use another code on the top of this encoding, maybe you could find a solution to against both side channel and photo injection. So because the linear code itself, essentially it can detect faults. That's the basic idea.
Okay, thanks. Any other
Thank you.
question? If not, then let's thank the speaker again. And this brings us also to our last talk in this session with the title Bit-Slice Masking and Improved Shuffling, How and When to Mix Them in Software. And the talk will be given by Olivier.
Hi, thanks Pascal for the introduction. Okay, so let's directly jump to the technical part of the talk. So here I will talk about side channel countermeasure and how, exploring a bit the design space of many different side channel countermeasure. And when you want to compare them, you require mostly two things. First, you want to evaluate them regarding to performances, and then you want to evaluate them according to security. So this is the two axes in the graph. So when you have an implementation, what you would like to have is a curve like that for one design, another curve for another design, where you have for a given performances, a given security, and then you set up the desired security and you pick up your implementation according to these curves. So here design one is the best because for a given security level, it offers you the best security. Of course, we are dealing with physical implementation, physical countermeasure. So it depends on some physical parameters. So if you change the platform, if you change the level, you have different curves. And maybe it's not design one, which is the best option, but now it's design two. Okay, so in side channel analysis, usually we have two big families of countermeasure. The first one is masking, where you randomize the data you process and you split them into shares, D of them. If you do that, you have some kind of a noise amplification effect where the security N you have in the end is the mutual information on the share set to the power D. And because mutual information is smaller than one, because there is some noise in your implementation, then you get an exponential increase in security with the number of shares. In this presentation, we will lay out the shares on the columns. Another family of countermeasure is shuffling, where instead of randomizing the data, you randomize the order in which you process the data. And to do that, essentially, you draw a permutation, and then all your execution flow will depend on that given permutation. So here, if we have a permutation of size eta, the impact on security is multiplied by eta. So here is a small example. Okay, so I draw a permutation, and then I execute. I process the data according to the permutation. Okay, so we have two countermeasures. We have shuffling, which is like adding some noise, and we have masking, which is amplifying noise. And then the question we ask ourselves in this work is, can we mix them in such a way that masking is actually amplifying the shuffling effect? So we get some kind of a eta to the D effect. So in the paper, we've been like discussing the cost versus security of this implementation. And of course, the first aspect is to explore security. So in this presentation and in the paper, we've been like exploring systematically the design space of shuffling plus shuffling, masking plus shuffling. And we did that with some kind of a paper and pencil approach, and then we confirmed that with simulation. We note that there is previous work by Riva et al. In 2009, where they were able to obtain some amplification of shuffling with masking for the linear layers, but not for non-linear layers, so for N gates, and that's a contribution of our work. The second part, it's about measuring the performances. So when you want to mask a given primitive, so you want to mask, let's say, n gates, how do you implement it? That do you shuffle? Do you mask more and so on? So we did some benchmark on Cortex-M4 platform, and based on that, we draw some conclusion about the cost versus security of these countermeasures. Okay, so I said we have two layers to protect. So let's first start with the linear layers. And what's the goal there? So here you have some data. So you have, oh yeah, perfect, it works. So you have here you have independent data on the rows, and on the columns you have the shares. So here in all the example already present, we have 5 independent data, and then we have 3 different shares. And the goal of protecting the linear layer is to do the component-wise addition. So you want to take the first component here, do the XOR with the second one, and then yeah, you put them at the output. Okay, so how do you shuffle these states which are masked? The first option is what we call shuffling tuples. So there, you just draw first a permutation, and then you select the independent data you want to process, and you process all the shares of that independent data. So here, yeah, use the permutation. So I jump to index 3, I process all the shares, then I jump to index 4, I process all the shares, then to 2, and up to the end. If you do that, you actually do not have amplification of shuffling with masking. The only thing you get is you get the factor eta, as if you were doing shuffling, as if you were doing shuffling in an unprotected case. And that's because an adversary can the only randomness is observed with shuffling is about what is the data process. Yeah. So we've been running simulation to confirm this paper and pencil approach, and that's what we see here. So basically on the x-axis for all the graphs, you have the noise level. So if you are on the right, it's noisy, and on the left is not noisy. And on the top, you have the mutual information estimation. And what is really important is what we have below, which is the security gain of our shuffling plus masking compared to masking only. And the horizontal dashed line stands for the eta we were expecting. So let's say here we are in the case where the gain is only eta, and we see that it's confirmed with simulation for all the parameter space we've been exploring. So it's not really satisfying, so we look for other option. The other option is what we call shuffle the shares. So here we just process the shares, the first share of all the independent data, then we jump to the second share, we process all of them, and then to the next share, and so on. And as soon as you process a new share, you will generate a new permutation. So here's an example. So I will process the first share. So I have a permutation, I process the first shares accordingly. And I jump to the second share, I process them accordingly also to the permutation, and then yeah, to the next one. If you do that, actually you apply shuffling to the shares. So you decrease the noise on each of the shares independently, and then because you are doing masking, you got the product of all the mutual information, and suddenly you get eta to the power d. So yeah, we got actually masking amplification of shuffling. And this is confirmed with simulation. So let's say we have a permutation of size 4, so eta equal 4. You have 2 shares, the gain we observe, so which is like the red parameter here is 16. And if you have 3 shares, you have like 3 shares and eta equal to 3, we gain a factor 27. Okay, so can we do better? Actually, for linear layers, yes. So what we can do, and that's what was proposed by Riva et al. In 2009, essentially, is you have all these eta to the d, eta times d, sorry, independent operation to do. So you can just generate a huge permutation on all these elements and then process them. Yeah. And then process them according to the permutation. I'm sorry, the animation is not that smooth. The pointer is a bit slow, sorry. And then, yeah, we get exactly what we had from Rivin et al. And we confirm that with some IT analysis. So yeah, we get the horizontal dash line and we observe the expected gain. So that was for linear layers. Of course, if you want to mask the AES, Keccak, or other block ciphers or other primitives, you need nonlinear layers. And here it's a bit more challenging. So essentially, what I explained for linear layers applies for nonlinear layers, especially it applies for shuffling share and shuffling tuples. And you got the similar gain. So shuffling the tuples for nonlinear layers, you get a gain eta, same for nonlinear layers. And for shuffling the shares, you got the same here. We were not able to extend the shuffling everything methodology, so the one by Rivin et al, to nonlinear layers, essentially because the permutation at the output of a masked and shuffled ISW is not uniform if you draw a too large permutation. And all the paper and pencil approach require to have a uniform permutation. So in the following of the talk, I will just focus on nonlinear layers because that's the most expensive part in masked implementation, and on shuffling the shares because it's the one which is providing us the amplification effect that we are expecting. Yeah, so that's it. Perfect. Now I'll jump into per versus security and explain kind of the trade-off we can have. So one thing you do if you want to protect a lot of AND gates, you can do bit slicing when you will do these independent ends in parallel. So bit slicing usually enjoys a large number of ends, and it enjoys processing them in parallel. And you have to spend some randomness to protect that. On the counterpart, shuffling also favors a large number of independent hands, but it favors to like a huge serialization such that you have, you can draw a large permutation and the eta factors become larger. And again, you have to spend some randomness on that. Okay, so the challenges are when you want to mix them together is, do you favor serialization? Do you favor parallelism? Do you spend your randomness on shuffling or on masking? Does it depend on the noise level, the primitive to protect, and so on? So that's what we study in the paper, essentially. So here I say there is different option. I will just give 3 different options. We explore a bit more in the paper, of course, but here is the 3 options I consider for TISO. So the first one is you want to do 64 independent ends and you have 32-bit register. One option is to do bit slicing, 2 times bit slicing on 32 bits. And you just do mask ISW multiplication. The second option is, okay, you have 2 independent ISW multiplication. You can apply the shuffling shares methodology on that. But what you can also do is to serialize a bit more and not have using 2 times 3D register, but you can use less the register, put 16-bit in each of them, and then shuffle that. So you do not have a permutation on 2 elements as here, but you have a permutation on 4 elements. So with this option, we can, we implemented that. We've been running that on, the implementation on Cortex M4. So we have performance number. We have derived the security with paper and pencil approach and simulation according to noise levels, permutation size, number of shares, and so on. So we actually have all the tools to draw the curves I was on the first slide of my presentation. So here you have the performances, so the number of cycles you require to do the end on 1 single bit. And here you have the security. So each of the plots will stand for different physical configurations. So on the left part, so here is you have a cheaper RNG, and here you have a more expensive RNG. And on the above is you have a low noise level, and below you have a high noise level. So you can draw option 1 when you do only masking. Each of the bullets corresponds to a different number of shares. Then you can do masking and shuffling together, so the option 2. And then you can do option 3. So what we see, not only on this setting, but also in all the settings we observed in the paper, is that pushing for serialization, so not fully use the register into your implementation, is kind of a bad idea. And it's systematically slower than fully using the register. So you should favor parallelism. So that's something. And then another takeaway is that we have these kind of areas where you have here the cost of the randomness, and here you have the noise level. And the question that this graph answer is, okay, should you do masking or should you do masking plus shuffling? And black means masking is faster. I mean, it's the most performant option for a given security level. So here it's 64 bits of security, light chain security. And we have also as parameter the number of independent ends you want to do. So this is for 128 independent ends, and then you can increase the number of ends and the areas here change. And you see that it's like the area where shuffling and masking gets better increases. So one more takeaway message of all our analysis is that we should favor using shuffling plus masking when there is a large number of independent ends, when the randomness is relatively expensive, and when there is relatively no noise. Of course, you have to put all that in perspective because all these parameters depend on platform and so on. So thanks for listening. The code for the simulation, so all the gain curves I've been showing earlier in this presentation are available on that GitHub link. Thanks for listening.
Thank you, Olivier.
Thanks.
So we do have time for a couple of questions.
For the linear layers, if I understood correctly, you are within the, so if you add two shared variables, then you would use the same permutation on the shares for both. Would it change anything if you permute them differently? Because it doesn't matter which shares you add up, if you can add the third share.
I didn't get your question, so can you repeat, please?
So you use for the linear layers the same permutation on the shares for the, if you add x and y, also if or xi and yi, then you use the same permutation on the shares, if I understood correctly. But you could use independent shares also, because it doesn't matter which of the shares you add. So you can take the first share of x.
Of course.
Does it change anything from the security?
We didn't explore that. But I guess then, I mean, if you use like, let's say Piney Notion, then you get like, you break some property.
I mean, if you're Piney, it's bad, but
if you are,
should be okay.
we didn't explore that. That might be a good track. Yeah.
Thanks for the talk. My question is, did your study consider leakages on the permutation in itself?
So that's a good question. So essentially, all the IT analysis I've shown here, I done without, I mean, we had an option in our code, right? And we discussed that in the paper. So either there is some leakage on the permutation, either there is no leakage on the permutation. And essentially, when there is enough noise, you get, I mean, it's as if the adversary was not able to get the permutation. So it doesn't care. It doesn't matter. The only thing is that, so we've been like executing some attacks on real devices, low noise one, and actually we showed that we are able to recover the permutation in one trace. So on these low noise devices, it doesn't work. But that does not mean that like it's not impossible to do. It's just like as usually in physical implementation, you have to take care of these physical parameters.
Thank you.
Yeah.
Are there any more questions? Okay, if not, then let's thank the speaker again. And Also, before we are leaving for lunch, I would like to remind you that we also have a lot of beautiful and nice posters around the coffee break session and so on. So if you have time, please take a look at them, talk to the people. I think they will appreciate it.